Good morning. In the last lecture, we looked at how we could highlight the edges. Okay, we had seen different techniques for enhancing the image, and one of them was to highlight the edges, because many times we want to look at the edges. They are the boundaries of object and background oftentimes, and we would like to be able to isolate the objects from the background. So today we will concentrate on this process, which is called segmentation. Okay, segmentation is basically subdivision of image into its constituents or constituent sub images or parts, which will be necessary for later on for recognizing the object, which is the ultimate aim, is to find what object is there and what are the properties of this object, how robot can interact with this particular object. That will be the ultimate aim. So for that we need to first divide it into image into subdivisions, which are hopefully corresponding to real differences between object and the background, or objects and different objects. So there are two approaches basically which are used for segmentation. Okay, the first approach is basically based on discontinuity. And the second approach is based on similarity. Okay, so let us look at the first one, based on discontinuity. So we are looking at now edges will come out to be useful. We have already seen how edges can be determined, and so if you look at it, we defined a gradient operator, okay, which was basically also a Sobel mask does that job very well. Okay, we have also looked at Laplacian mask. Okay, these two can be used to identify edges. Okay, let us now just look at that. Supposing I have a object which is bright and say the background which is dark. Okay, object is bright. Now what one can do is, first of all, one can apply the Sobel operator to this image. Okay, so you will get the at various points in the image, say this is point P, I can find out at point P what is the gradient of the image, and if the gradient is large enough, okay, so I can compute G at point P, and if it is greater than some threshold value, some threshold number, that, because what you remember is that gradient operator, when the intensity changes, suddenly gives you a large value. If the intensity is uniform, then it does not give you a very large value, it gives you close to 0, right. Of course there will be variation from one point to another point, some small variations will take place continuously because of diffuse lighting. So but those will give out to be very small numbers, but at the edge, anywhere near the boundary, if you take that mask and run that mask, then you will find that the value comes out to be very large. Okay, so coming back here, if you have the gradient determined at each of the points, and if it is greater than some threshold, then this is likely to be a boundary pixel. Okay, now what we want to do is we want to join all the boundary pixels together. What will happen is, because of variations in intensities, we will not always get all the boundary pixels, so there will be some missing parts, or we will get too many boundary pixels near if the boundary is thick or there is a shadow, So there can be number of effects like that. So one technique is to link the edge, so it's called edge linking. Okay, obviously as the name suggests, we are going to link up the edge pixels. So what we do is we look at what are the similar, which are the candidates for forming the edge. So what we do is we look at two things. We look at one is the intensity, or the value of the gradient, and one is the orientation of the gradient. So value of the gradient is what I have said, and then orientation can also be found is some theta, which is tangent inverse of gradient in the y direction divided by gradient in the x direction, right. This gradient that I am talking about is, say, gx squared plus gy squared square root, or it could be, or you could also approximate this as gx plus gy, absolute values, right. Number of ways you can define what the gradient at a particular point is. It's going to depend on the change of intensity in the x direction and y direction, because edges are not always going to be aligned to x or y directions. So we'll have to need to know the value of the magnitude of the gradient. Okay, so what we simply can say is that if g of x1 y1, which is one of the pixels which is likely to be a boundary pixel, this minus x2 y2, another neighboring point, okay, if this is less than some number, okay, so some delta, let's say, if this is less than some delta, then what we are saying is that the intensity of the edge is almost the same. That means it's likely to be belonging to the same edge. So that is one condition, and that theta 1, let's say, minus theta 2, absolute value of this is less than some delta, let's say. So if you look at edges, points along the edges, what this theta is, of course, a normal. If we are taking various points, and this point will also have the same direction, so that's why we don't care whether it's along the edge or not, but it is connected to the edge, and basically if the gradient direction and the magnitudes are similar, then we will say they belong to the same edge. So we'll link these together, we'll put it in the same set. Okay, that's one way of doing it. Now another possible way of doing this is to also use Laplacian operator. Okay, so what we can do is we have some or let me make the edge of a brighter object in darker background. So if I look at simple situation like this, where you have dark areas and a bright object, then we know that if I look at the gradient along the y direction, if this is my y direction, this is my x direction, then gy is going to vary as, okay, first of all, how the intensities are varying. So let's look at fxy. Intensities as I go along the y direction, say I take a line and I go along that, and then I will see that the intensities are low. At some point the intensity will rise, then they will have some high values, and then it will fall down again. So intensities are like that. So therefore the gradient in the y direction is going to be looking like 0, and there will be a peak here, then 0 again, and a negative kind of a peak existing here. Okay, if I look at the Laplacian operator, that is going to give me the second derivative, and that will show me a high value here, then a high negative value here, high negative value here, and high positive value here. Okay, so this will be the Laplacian of the Laplacian operator result. Now what I can say is that if for bright objects, okay, the sequence that I expect is that, no, first of all let me define 3 levels of intensities. So first of all, I'll say that the transformed image Sxy, I'm going to say that it is 0 if my gradient is small enough, if it's less than some threshold, and it's positive or some gray level if G is greater than or equal to threshold, and okay, if the Laplacian is greater than 0. Similarly, I will call it a third level or minus level if gradient is greater than the threshold and Laplacian is less than 0, right. So I am now distinguishing different parts of the edge, as I scan through along the x direction or y direction, I will find a pattern like, so for this bright object in dark background, now what I expect is that there will be something, then there will be a plus followed by a minus, okay, then there will be zeros or minus possibly, okay, and then I will have a minus followed by a plus, and then I will have whatever else, right. This is typically what I'll expect if I have a bright object in dark background, if I go along x direction or if I go along y direction. Now this will help me to remove, see what happens is that when we actually do these processing in real images, then we find that the effect of noise is that we will find spurious edge pixels which are not actually there, but they are because there's some kind of reflection has come or some problem in sensing is there, that there are noises present. Now we want to remove these noises and say zero in on the edges which are belonging to the boundaries of the object with the background. That is the purpose. So one way we saw was that we can link edges which are having similar gradients and which are having similar directions, right. Once then I know that pretty much it must be belonging to the same edge. Alternately, since I know this is the kind of sequence that I expect, if I divide the image into 3 gray levels, some value, some another value, then I know that I expect this sequence. So I will be able to say that the edge belongs here and here, this is the object and this is the background, okay. If a few noisy pixels here and there are not going to change the result that I am getting here or my conclusion here. So that is the basic idea, okay. Now oftentimes we are interested in the image. Okay, so straight lines amongst edge pixels. Okay, why would we want to do that? Supposing there is a box shape object, or there is a nut lying on the table and it has some straight edges. Okay, maybe there is some kind of an object like this. So we would like to know what is the orientation of this. So we would like to know where, if there are straight edges present. Okay, so if there are straight edges present, how do we find it? One way would be to go and say, okay, x1, y1, etc., yn, these are my probable edge pixels which I have determined because I use Sobel operator. And then I say, okay, I take pairs of these. So from x1, y1, x2, y2, I can find out the slope and the intercept of a line which passes through them, right. So I can find out from all these n times n minus 1 divided by 2, okay, combinations which will result in some value of the slope, let's say call it a, and intercept, so let's call that b. So this is slope of line, okay, defined by xi, yi and xj, yj. Similarly, this is the intercept value. Now, what I need to do is, given one line that I have defined using 2 points which are possible edge pixels, then I would compare it with all other x and y values and see whether they fit also with the same line or not, right. So, this way I will, this is approximately n squared order. If I do the comparisons with all other points, then it becomes n cubed order, okay, order of comparisons or evaluations required. Now, this number tends to be pretty large. Okay, so what one does is, one can use instead a technique which has been developed by Hough, okay, and it's called Hough transform. Okay, what is Hough transform? Let us try to understand that. Now, let us look at our xy plane and say I have a point here with some coordinates xi and yi. I can pass number of lines through this point, right. If I pass a line like that, then I know that it has some slope and it has some intercept. Okay. So, this is, let us say, line A, and now if I look at a plane which is defined as, this was defined by x and y, this is our regular Cartesian plane. If I define a plane which is defined by A, which is the slope, and B, which is the intercept, then I will call this AB parametric plane. Okay, this is my xy regular plane. Okay, what I am saying is that given this particular line A passing through the point xi yi, the slope that I have is a negative slope here. Okay, so I will have some value here, let us say negative slope, and some intercept which is positive. So, I have a point somewhere here corresponding to this line. I have a point, so I will call that A, right. Now, I take another line, let me take a line which is, say, horizontal, passing through the same point xi yi. So, I have slope is 0, so I have slope 0, intercept is some positive number, intercept is some positive number. Okay. So, I get another point, let us say this is B. Let me take a line, let us say, passing through the origin. So, let me call this C. Now, C has got intercept of 0 because passing through the origin, right. So, it is, and it has got some slope which is positive. So, in fact, what I can show is this is point C is here, right, because my line, okay, if I am given a point here, I am going to be able to write this parametric equation of that particular point xi yi. So, xi yi point, okay, gives rise to or can be represented as a line in the parametric plane. Okay. So, this is going to be given by, in fact, okay, it will be given by, because the equations of a line, equation of a line is ax plus b. Now, what I am in, all I am doing is simply rewriting it in a different way. So, I will call this, why not I write it as b is equal to, right, minus x times a plus y. It is the same equation, I have now transformed it. And what I am saying now is, now I substitute for xi yi. So this equation that I have got here, okay, is nothing but b is equal to minus xi times a plus yi. Okay, interesting thing is that each point in the xy plane corresponds to a line in the parametric plane. Okay, if I take some other point, so let me take one more point here. So this is my, say, xk, yk. Once again I can find infinity of lines passing through this point, and they will all fall along a straight line here. Okay, as it turns out, I will get say, let's say my 0 intercept here will be a line which will be, let me show it as dotted line, it has a slope, and 0 intercept, right. And I have a horizontal line which has got 0 slope. See, this had 0 intercept, this is 0 slope, and here, okay. And likewise I can, this was that. Now this line here is b is equal to xk minus xk times a plus yk. So every point, a point in xy plane transforms into, okay, a line in AB plane, or infinity of points in AB plane. Now look at this, we have 2 points and these correspond to 2 lines and they intersect at this point, right. This is nothing but the line which is common to both xi yi and xk yk. So this in fact represents a line which is joining, passing through both of these points. Now we will use this idea to say that if I have a image and I have already identified some boundary pixels, so from those boundary pixels, if I take one by one each of these boundary pixels and apply this transformation to get the corresponding line in the AB plane, I am going to take each of the boundary pixel xy location and find corresponding to that the a and the b values. Then what I will get is, I will have a image. Now I have now transformed this into some graph, or in fact what I am going to do is to discretely divide my a and b values. So I have some a minimum, a maximum, okay, b minimum and b maximum, and I have compartmentalized this, I have divided these values, meaning I am discretizing slope, and I am saying, okay, any slope which is between 0 and say 10 degrees is going to be one category, 10 degrees to 20 degrees will be another category. Similarly, I will say that every intercept which is 0 to 1 will be one category, 1 to 2 will be, or whatever the interval I choose depending on what is the kind of accuracy I want in detecting or finding straight lines in the image. Then for given point which is a boundary pixel, okay, I am going to take some value of a min, find out the corresponding value of b min, whatever that corresponds to, I will put a dot in this particular box. Then I will go with the next value of this thing. So I will get various dots in these boxes, okay. I will take then one more point and find out the whatever dots come into these boxes. So now I'm doing far fewer calculations, because depending on how finally I have resolved this a and b parametric plane, I will find that there are some boxes which are heavily dotted and some are sparsely dotted, okay. So what the meaning of this heavily dotted box here will be, that this value of a and b is actually common to a whole lot of points, which means a point in the parametric plane actually corresponds to a line in the xy plane. So this means there are a whole lot of points which belong to the which lie on the same straight line, and this is basically the approach of the Hough transform, that you discretize a and b parameter, then you find out where the maximum number of points are, those are corresponding to strong or large straight segments. Now one problem that one encounters in this approach is that if you have a vertical line, if you have a vertical edge in a picture, then we cannot easily find the a b parameters, because both a and b are infinity for a vertical edge. The intercept is going to be infinity and slope is also infinity. So we run into a problem with vertical edges. One can get around this problem by simply saying that, okay, let me define a different type of transformation. It's also Hough transformation. So I take a point now. Instead of finding a straight line parameterization, a b parameterization, I will find a parameterization now. Supposing I pass a line through this point, which is what I've been doing, then I'll say, okay, let me now characterize this particular line by a perpendicular dropped from the origin onto the line. Okay, this is now going to be characterized by some theta and some rho value. I can pass another line through this same point, and I'll find that I have parameterization now rho. Okay, this will get around the problem that if there are vertical edges, there is no problem now, because if I take a line, vertical line passing through this, okay, the perpendicular drop will be this, and this will be the rho, and theta will be 0. Similarly, horizontal line is no problem. So the relationship between rho and theta and xy, okay, simply can be written as this. You can show geometrically x times cosine of theta plus y times sine of theta. Okay, so what this means is that given a particular point, rho theta parametric plane, now I am going to have some kind of a sinusoidal curve. Okay, depending on the values of x and y, if I change theta from in the range of 0 to 200, 360 degrees, then I will find that this is going to be a repeating function. In fact, I don't need to go on up to 360 degrees. I can chop off, I can take the area from 0 to 180 degrees, because after that the curve is going to be predictable. If I know this much information, I can do the rest of it also. There is no problem. So what is now going to happen is, my transform is now going to be such that corresponding to each of these values of x and y, which are belonging to the boundary pixel, once again I am going to have my parametric plane in which I am going to have theta min, theta max, which is likely to be from 0 to 180 degrees, and rho max. Okay, or I can take from minus 90 to plus 90, so that I can have 0 here. Now I subdivide that region, parametric plane, into boxes depending on what accuracy once again I am looking for, and I carry out the same procedure that given a boundary pixel x I y I, I take various values of theta depending on how finely I have resolved it, and for each value of theta I can correspondingly find out the value of rho, and I point for each value of theta, I then plot this, and I am expecting to get sinusoidal type of variation here approximately. And once again, for different points that I take, I am going to get different sinusoidals, and whatever number of sinusoidals, I will find that there are some points which are intersecting these curves, different curves. Correspondingly, I will get once again different number of points in the same box, right. So, this way once again I can find out which are the points which lie on the same straight line, the value of the slope, etc., and that can be known from the value of theta and rho. So, this way I have to, if I do not have very fine resolution here, then it gives me a advantage in terms of number of computations or comparisons which are required. Okay. Now, all these procedures that I am describing right now, I mean they are quite prone to noise present in the picture. So, let us look at one scheme which is immune from noise. So, this I will call detection. Okay, idea here is that we define a cost function. So, if I have say 2 pixels, say P and Q, if I go from P to Q, then what is the cost associated with this is something that I want to use. So, if I define my cost P comma Q equals to some value minus the difference between FP FQ, okay, then this is the intensity at P. At P, this is obviously intensity at Q, and Q is a neighborhood pixel. We could consider 4 neighbors. Okay, so this is a 4 neighbor here, and what I will choose this H to be typically the difference between intensity values or maximum difference between intensity values between object pixel and background pixel. Okay. So, supposing the edge was passing through here, this belonged to the object and this belonged to the background or vice versa, whatever, then what will happen is this Fp minus Fq would be a large number, as large as H, right, or in the same ballpark figure, order of magnitude. And when you subtract out this difference from this constant value H that I have taken, I will get a very low cost. So, going from P to Q, I have low cost here because the boundary existed between them. If the boundary did not exist, it was the same background, let us say, then Fp and Fq are going to be similar values. So, this difference will be almost 0, therefore, I will get a large cost here. So, I am just saying simply defining a cost function between 2 pixels, and what I need to do now is to say I have a start node. Okay, so, now the procedure is start at a node, call it start node or beginning node, and then I have a terminal node. We want to end up at terminal or end node, and I want to find out the cost of different paths that I take from beginning to end. So, if I have now some image, I say start from this pixel, then I can go, this happens to be corner pixel, so I can go this way or that way. I have only 2 possibilities. Then I can go from here in 2 directions. Once again, this direction I need not go because I have already covered that, but once I come here I have 3 directions to go to, right. So, I am going to get a tree structure depending on how I start. I start here and then I get 2 possible places, then I may get 2 other possible places. Similarly, and then after that I may have 3 possible places. So, I am going to get a tree structure, and this tree structure will be fairly dense depending on how many pixels that I have to cover. If the image is 500 by 500, then the problem with this technique is that it is very intensive in terms of computation. The combinations that we have to consider of different paths. Basically, we are looking at all possible combinations of paths going from one point to another point. So, there is going to be a very large number of such paths. So, whether I go this way, this way, this way, this way, or I go this way, this way, this way, this way, any number of such paths are available from going from one point to another point. And I will compute the cost for each of these paths, and I will say whichever is the minimum path is the best boundary. Okay. So, advantage here is that I am not very much dependent on 1 or 2 pixels being wrong, because overall the cost is going to be will turn out to be the lowest if I am generally going along the boundary. Okay. But as I said, the disadvantage is that there is far too many paths available. So, one actually does, instead of getting the optimal path, one sacrifices that and tries to have some kind of a trade off between how much time it takes to compute it and whether we are going to be very optimal or not. So, one can have schemes in which one looks at suboptimal sub-regions where you have found out some optimal path, and then you assume that the whatever is the optimal is, it's not going to change because of the rest of the image, which is not strictly true. Okay. But your combination of local and global can reduce the overall computation and give you fairly good results. Okay. Then let us look at, see, we have been looking at boundary based segmentation. We can look at now the second type of segmentation, which is based on similarities. Okay, in similarities, first thing let me consider is thresholding. Okay, thresholding, as you will know, is you select a critical value of intensity, and then anything above the critical value will be taken as one region, everything below would be taken as another region. So, we are generally talking about images in which there are objects, and we are not looking at surface features so much as what is the boundary of the object versus the background. So, if I define a threshold T, and so one possibility is that T will depend on the intensity value or distribution in the whole of the image. So, if I have some image, now I am not going to try to draw image actually, but I have various intensities at various pixels. Okay. Now, depending on this intensity values, I select some value and say, okay, anything above that is going to be 1, everything below that is going to be 0. So, then I can threshold, and this is called global thresholding. On the other hand, this technique is not going to work very well if you have different objects which are lying in different areas with some change in the background intensities, there are shadows. So, what will happen is, supposing I now look at sub images of the image. Now, this is not actually a pixel, there are many pixels inside each of these regions. So, I can do some local analysis here and say, okay, in this local region what is the best threshold, in this local region what is the best threshold, and these thresholds will vary depending on how the scene is, right. So, if I do that, then my threshold becomes not just a function of the intensities, but some property that I am looking for in neighborhood of xy, which I am calling it some local property, and it will also of course depend on the individual pixel intensity level to decide what is the threshold, right. Then this is called a local threshold. Finally, I can have a dynamic threshold which not only depends on these two, but also depends on the individual pixel locations. Then this is going to be called a dynamic threshold. Okay. Now, for thresholding, basically what we do is, if I take a simpler situation, if I look at the distribution of pixels in different intensity levels, so I look at the probability distribution function. So then I will have, say, objects look like this, and say the distribution function for the background, say, is something else. So I will have some kind of a probability distribution functions corresponding to, say, object, say this is the background, right. Then what we do is, we can select a threshold here, which will be the best way to distinguish the object from the background. Mathematically, I can say that if P1 times, this is, let us say, P1 of R is the intensity value, and this is the number of pixels in that intensity value, times P1 of at threshold should be equal to P2, capital P2 into small p2 at threshold. This is small p2. Now, capital P's are what are called a priori probabilities. Okay. This is known from the general situation. Supposing I have a conveyor belt in which you have some parts coming, then I know that one part on the average comes every 5 seconds. So, given any scene, I will have on the conveyor belt, I will have 3 parts, let us say. Area of the conveyor belt is so much, area of the parts is so much. At any given time, I expect 3 parts, which means, corresponding number of pixels at any time are expected to be object pixels, and the remaining are expected to be background pixels. So, if that is the case, then I can multiply these with the probability distribution function of each of the objects, and then I can pick my threshold in this fashion. One can go more and more in details of these, but I think we will not have time to do all that. So, let us get some more flavor of some other techniques. Okay. So, let us look at one more technique based on similarity, and which is called region oriented segmentation. Okay, what we want is, we have an image, we have various objects in this, we would like to divide, we will have to define these as some sub regions. Okay. So, let us say this is R1, this is R2, this is R3, and so on and so forth. So, what we want is basically that union of all the regions, I going from 1 to whatever number of regions are there, should be the total region. So, let me say this is the total is R, okay, and I am going to define the region so that each of these Ri's, okay, is connected. Now, definition of connected we have already seen in the introductory lectures, where some kind of a property, maybe intensity, is belonging in some range, right. So, each of the regions should be connected, but if you take 2 regions Pi, okay, and first of all they should be distinct. So, if I take Pi and take intersection with Ri and Rj, this should be 0, there should be no pixels which are common to two regions, okay, and then they should have some property. So, this is some property of region Ri, it should be true, otherwise we will not be able to call it a region. And similarly, property of, if I take 2 regions together, then it should be false, right. So this is what I am calling a sub image or region within a image, which are defined or which are characterized by this type of a set of properties. Okay. Now in one simple minded scheme, what I can do is I take a look at that. So if I am looking at 4 neighbors, then I see at this point. Okay, if it is belonging, it is having the same property, whatever the property I am going to define a region, then I will say, okay, this is belonging to the same set, belonging to some Ri. So this is called a region scheme, whereby I look at the neighboring pixels. If the properties are similar, then they belong to the same region, and I keep on going until I encounter a boundary where the properties change, and therefore I will not be able to go any further. I will not be able to grow the region any further. Then I'll have to start with another seed point at a different part of the image, and I start growing it all around again. And then, so this way I will put the seeds and I will find out all the different regions in the image until I cannot find any new, and there are no more pixels remaining after that. Another alternate scheme is what is called region splitting. And let me say, and merging. Okay, the basic idea here is, let me illustrate that by taking an example. Say I have an object here lying in the image, and say this is some intensities which are very different than the background. I am not coloring it because then it becomes very difficult to see. So what I do is I have this region as the whole image first. I check for the property of this region R, and I find that this is false. What I mean by that is that if I look at various parts of this particular region, I find that there are different properties. There is no single property which is, or whatever property I am considering is not uniform, right. So then I take this region and I subdivide it into subregions. Say I divide into 4 equal subregions, and then I look at, this is my R1, this is my R2, this is my R3, this is my R4, and I find out the properties at R1, and I find this is false, but property at R2 is true because it is a uniform region. Okay, all pixels have similar intensity values or properties, and this is, and similarly I will find that this is property at R3 is also false, property at R4 is also false. So what I am doing is I am starting out with the whole image, then I have subdivided into 4 nodes. R1 is false, so I need to subdivide this into 4, but R2 is true, so I don't have to subdivide it anymore, whereas the other R3 and R4 I will have to subdivide into smaller and smaller square. So I have chosen so that these boundaries are matching. Okay, if they will not match, which means we will have to do further subdivisions, right. So once I have done this, now I have this as, say, R11, R12, R13, R14, and each of these now have uniform properties, okay, because this has dark, this has dark, this is dark, but all others are bright. So we have, now I don't have to split anymore. Now my time for merging starts here. So I will now consider R11 and R12, which are neighboring regions, and I find that they have the same properties. So I remove this boundary, I define this as a region. Similarly, I will start looking at all these subregions, and I will find that the background is now one region, and the object is another region. Okay, this is called a quad tree. So I think we'll have to stop more or less here. What we have seen is, in this part of the course, we have seen that we can look at scenes, we can acquire images, then we can relate the pixels which are there in the camera frame or camera frame of reference and relate them to the external world frame of reference. And we saw perspective transformation in that. We have also seen stereo images, how we can get information about the depth, right. The problem is that imaging transformation is basically a 3-dimensional transformation to 2-dimensional imaging, 2-dimensional image, and therefore some information gets lost, and the same pixel in the image corresponds to infinity of points in the real world, and therefore we need some additional information when we want to go and reconstruct the world from the image. So either you have to have 2 images and need to know corresponding points. Okay. We also looked at the camera calibration problem. Then we looked at a number of image smoothing operations, okay, which is basically all part of pre-processing. We looked at some enhancement techniques, which is basically highlighting the we looked at histogram based approaches, and we looked at edge enhancement approaches. And then what we have looked at is various segmentation problem, how to divide the image into various segments or regions which are corresponding to objects and backgrounds. Now from here there is a whole lot of other things remaining, which is that once you given a particular object, how do you now recognize the object as a region as a object. So one will have to now start defining properties for each of these objects, each of these regions I should say. You can have area as a property, you can have orientation, you can define boxes which will enclose it, so or you can define aspect ratio, you can define centroids, you can define the shape in some way of how you have to traverse the boundary to enclose the object. So there are a host of different properties that you can find out, and then based on the properties one can determine what the object is. So it leads to then recognition of the object. So if I am trying to compare say washers and bolts which are coming on this conveyor belt, I have images of those, then there are different properties which will distinguish these two. So I need to define those properties depending on the object, and then I can process the image, find the region, look for those properties. If the properties match, then I have a good confidence in saying that this particular region belongs to a washer. So this is a washer. Now I have recognized a washer, I can find out other properties of that, and then I can have tasks which are connected with robot movements, which will then use this particular information that the object or a washer is present at such and such location in the image, which I know where it corresponds to in the real world, because oftentimes the z distance will be known. If it's a conveyor belt and a camera hanging above, then we know the distance between the camera and the plane in which the objects are there, and therefore we know the z absolute global z location, and therefore we can now connect the x and y location of the outside world from the image points. So this is in a nutshell I have given you how image or machine vision can be useful for robotics. This is by no means exhaustive, and there are so many things that one can talk about in this, but simply we don't have time to cover all of those in the course. Thank you.